Okay, ladies and gentlemen, welcome to Chapter 5. So that joke used to be a lot funnier before Cosby was a rapist, but sine B over tan B equals Cosby. It's kind of funny now, but not in a ha-ha way, more like a woo kind of way. All right, let me rearrange my camera here. Again, trying to make sure my butt doesn't play an inordinately large role in the video. All right, so trigonometric identities. An identity is something that's always true. It's an algebraic expression typically. You know, like 2x plus 2 equals 2 times the quantity x plus 1. So an identity is some equation that's always true, no matter what I plug in for x. So a specific subset of all the identities in the mathematical universe are the trigonometric identities. And those, of course, include at least one trigonometric function. So our task today is going to be to identify and use basic trig IDs to find trig values. Use basic trigonometric identities to simplify and rewrite trigonometric expressions. So in years past, I had kids laboriously copy down all these exhaustive lists of trig identities. And I've since decided that wasn't the best use of our class time. So what I do now is I've got a document that's got all the identities on it, front and back, and I'll just attach it to this assignment. So you guys can print that off if you're a print off kind of person, or you can have access to it on your device digitally. So in other words, you don't have to write down all these as we encounter them. All right, so an identity. This is an equation that's always true. Always true. No matter what I plug in for x, it will be true. And so much of mathematics depends on identity. So a trigonometric identity is an identity that includes at least one trig function. So there are families of trig identities, and they're based on various mathematical relationships. The first of those families we want to discuss here is the cofunction family. So I don't know if when I was graphing the sine and cosine, if you guys made this connection. But if I graph the sine, you remember it's kind of like this. And if I graph the cosine, it's kind of like this. Oops. So let's see. Yep. So I don't know if you can see it, but each is the other phase shifted a little bit. So they have the exact same shape. They're just horizontally translated between the sine and cosine. So that relationship brings about a family of identities called the cofunction identities. So these relate to the sine and cosine having the same shape. So sine x and cosine x are horizontal translations of each other. So that gives us the family of cofunction identities. And then we have odd even identities. So if you look at sine of x, once again, we see that it is symmetric to the origin. So it is an odd function. And that gives us a small subset of identities. And if we look at cosine of X, and if you can't just sketch these off the top of your head, then you're not quite where you need to be. And I'll just graph one period of the cosine here. We see that it is even symmetric to the y-axis. All we need to know that is right around the origin here. So again, we have some identities that result from that evenness of the cosine function, symmetric about the y-axis and all that. All right, any questions about anything we've talked about? Okay, cool. So there are many other families of trig identities, but these are two the book identifies as ones you're probably not familiar with. So reciprocal and quotient identities. Now this is something we've talked about all throughout chapter 4. So this is not a new idea. Remember when I graphed them? In every case, I gave you the reciprocal identity to help you understand where the zeros were and vertical asymptotes and so on. So we've talked about some of these relationships pretty significantly thus far, but these are called the reciprocal and the quotient identities. And the one that we use probably the most is tangent is sine over cosine. We use that very frequently. And often when we're simplifying trigonometric expressions, one sort of the default strategy I have, if no other strategy presents itself immediately, is to rewrite everything in terms of sine and cosine and look for things I can factor out or cancel, or factor out and then cancel and so on. So using these to rewrite things in terms of sine and cosine, which would be these, are very frequently used. So these are things you need to have in your noggin. So using reciprocal and quotient identities, if the cosine of theta is 3/4, find secant theta. So in chapter 4, we would have created a reference triangle. Then we would have used the information that secant is the inverse of the cosine. So it's going to be hypotenuse over adjacent. Then we would take from our reference triangle the hypotenuse and the adjacent and plug those in and problem solved. But in chapter 5, we need to use the reciprocal and quotient identities. And that tells us that cosine theta is 1 over secant theta. So we'll plug that in for cosine here. And then we're going to take both sides to the -1 power to get this. A little more efficient, maybe. So we have more powerful tools in chapter 5.
So you basically just flip them both sides of it?
Yes. Mm-hmm. So taking something to the -1 power reciprocates both sides. In other words, point. So this side becomes secant theta over 1, and this side becomes 4/3. Good question, Rachel. Other questions? Okay, so nice, easy start to chapter 5. Part B, if secant of X is 5/4, and tangent of X is 3/4, find sine of X. So we're going to use some of those reciprocal and quotient identities. We know that secant is 1 over the cosine. And we know that the tangent is the sine over the cosine. can't use that one on the right just yet because there's still two unknowns. But I can solve for, and I use X here, I use theta here. I need to be consistent. Whatever the argument is in the beginning, try to keep it the same throughout. Just makes your problem look better. Okay, so we can solve for the cosine here, plug it in here, and then we'll have an equation with one unknown that we can solve. So once again, reciprocate both sides. And then we'll plug it in here. So we get the sine of X over 4/5 equals 3/4. So if I multiply both sides by 4/5, on the right, the 4's cancel, and on the left, that cancels out the denominator, and I get sine of X equals 3/5. So that's an example of a problem where a reference triangle probably would have been more efficient, but we're going to humor Fivehead and do it the way he wants us to do it in chapter 5. The application of those identities. So the identities I applied were from this step to this step. I used the secant X equals 1 over cosine X. Remember, that's always true. And then over here, I did the tangent X equals sine X over cosine X. Another identity that's always true. So that's the part where we applied the identity. The rest of it's just algebra.
Okay, on the top left, you forgot the C, so it looks a little interesting.
Ah! Good eye, Rabbit.
I just don't want you to put that up there for the notes and then be in there forever.
Thank you, sir. You saved me some potential grief there. Yeah, if you leave the C off of secant X, you got a problem.
Other than that, I'm good.
Thank you, sir. Other questions, comments, observations? Okay. So the answer is 3/5. And again, we could have created a reference triangle and found it faster, but we're trying to exercise our application of identities. So here's one for you. If I know that secant of, and actually this is a bad example, so I'll go ahead and work it out. We're going to find sine of theta. The reason why it's a bad example is this. The secant is equal to 1 over the cosine. So the application of a identity will not solve this problem. 1 over cosine theta is 13 over 5. So cosine theta is 5 over 13. But we still have to use a reference triangle. So they're forcing us to use the old techniques because you can't get to sine from the cosine without more information, or so there probably should have been a second one here that they left off, but that's okay. So we'll make a little reference triangle. We still got this technique in our back pocket. The adjacent to the hypotenuse is here, and so 5 squared plus b squared equals 13 squared. 25 plus b squared equals 169. B squared equals 144, B equals 12. So sine is opposite over hypotenuse. Student example shouldn't use different techniques from the ones I just did. But it's often the case. And really, as flawed as this textbook is, it's still the best one I've seen. Textbook manufacturing is Not great in America. It's almost like they just want to put some crap out and sell it. And they're not worried about whether anybody can understand the material or not. And the notion that we need a new version every 5 years. You know, when this math was developed, the newest, this math is thousands of years old. Thousands. The newest of the mathematics we study is at the very least 300 years old. So there has been no change in this material in 300 years. And we're expected to believe we need a new version of the textbook every few years. Come on. Indeed. And they sell it by saying that, you know, pedagogy is what really changes, you know, the methods of instruction. Okay, so let's talk about Pythagorean identities. So these are probably the number 1 or 2 most used identities. And here's the daddy identity. Sine squared plus cosine squared equals 1. Sir?
Were these the ones that are already on there that we don't need to write down?
Yes. But you should make a mental note that Pythagorean, or at least write down this, Pythagorean identities are very commonly used. And they come from the unit circle. So if I'm looking at the unit circle, you know, I've got a point here, and it is the cosine of some theta, the sine of some theta. And if I took the associated triangle, you remember how we developed the points on the unit circle. So if I consider this triangle, you see how the x side is cosine of theta, the y side is sine of theta, and then the hypotenuse is 1. So if I apply the Pythagorean theorem to that triangle, I get right here. These two are algebraic manipulations of this. So this is the fundamental idea in Pythagorean identities. And whenever you see a trig function to the second power, your knee-jerk reaction should be to apply a Pythagorean identity. So Pythagorean identities are the way to go when you have a squared trig function. Now, this is where that notational inconsistency comes into play. If you have a little superscript after the function like this, and it's anything other than -1, then it means the trig function raised to that power. So let me talk about that just a second. So if I have sine squared theta, that means the whole function raised to the second power. If I have tangent cubed theta, that means tangent of theta to the third power. And so on. Any number except for -1. But if I have sine -1 of theta, that is not equal to the sine of theta to the -1 power. This, you see how this is an inconsistency? This means the functional inverse, not the reciprocal. So this is, again, a notational inconsistency. That's why I prefer the term arc sine. But something to make note of, this is an inconsistency in notation. It's a flaw in our mathematical notation that doesn't work out to be the same. Let me know if you guys have any questions. All right, Pythagorean identities. Let's apply them, shall we? So we have cotangent theta equals 2. And cosine theta is negative. Not theta 0. So we have a positive cotangent. That's only the case in Q1 and Q3. Cosine is negative. Well, that's only the case in Q3. So I know theta is in quadrant 3 by analyzing the sine, S-I-G-N, of the cotangent. It's positive. Cotangent is cosine divided by the sine. So the cosine and the sine must have the same positive or negative sign, S-I-G-N, for the ratio to be positive. And that's only the case in Q1 and Q3. And then they tell us the cosine is less than 0. So that's, of these two that are possible, that's only the case here in Q3. So that's what forces theta to be in quadrant 3. You need to get used to doing that quadrant analysis when we're extrapolating from information of theta is important, because now we know sine is negative as well. And we would not have known that without this. So it would have often been the case that somebody gave me the sine and cosine here positive, kind of disregarding this, if they didn't do the quadrant analysis. So both of these are going to be negative in this case, sine and cosine. All right, so with that out of the way, when we square something, you lose the sign, S-I-G-N. So negative 2 squared is 4, 2 squared is 4. What sign was it in? If you have the square root of 4, what is it, positive or negative? Who knows? So that ambiguity is why this is necessary. So we want a Pythagorean identity that relates to cotangent. And conveniently, they've given us one here. Cotangent squared theta plus 1 equals cosecant squared theta. But what I usually do is take the daddy, which is sine squared theta plus cosine squared theta equals 1. And then I algebraically manipulate this to create whatever I need. So I see I need cotangent. Remember that the cotangent is the cosine over the sine. So if I divide everything here by sine squared theta, I'm going to have a cotangent in the middle. So this becomes 1. This is cotangent squared theta. And then 1 over the sine is the cosecant. So that's cosecant squared theta. So the only one of the Pythagorean identities I memorized is this, because it's just so easy to derive whatever you need from that. So that one's like the granddaddy of all Pythagorean identities. And then we use all these little grandchildren. And you'll see that the one I derived is the same as this, with first two commuted like so, but it means the same thing. So let's plug it in here. So 1 plus cotangent squared theta equals cosecant squared theta. I'll plug in that 2. 1 plus 2 squared equals cosecant squared theta. So that's 1 plus 4. And then 5 equals cosecant squared theta. So cosecant theta is going to be have the absolute value of the square root of 5. But remember, we said we're in Q3. So that's why that's negative. So everywhere I apply that, I'll try to highlight it like so. The reason why it could be either positive or negative when I take a square root. I know it's negative because we're in Q3. Actually, you know what? I hate that highlighter color. It's way too dark. There we go. That'll be better. So now I have the cosecant. Why is that valuable? Well, remember that the cosecant is 1 over the sine. So sine equals sine of theta equals negative 1 over the square root of 5, which if I rationalize here equals negative radical 5 over 5. So there's part of our answer, and we've arrived at this without using any chapter 4 techniques. We're exclusively using identities. So going forward, if we want to solve this, continuing to use only chapter 5 techniques, we know that sine squared theta plus cosine squared theta equals 1, going back to the original identity. And here I know sine squared theta is going to be negative radical 5 over 5 squared. And so that's going to be negative 1/5, no, positive 1/5. Yeah, because square root of 5 squared is 5. 5 squared is 25, so 5 over 25, which becomes this. And if you have a complicated expression like that that's difficult for you to calculate mentally, you can always rely on good old calculadora. So negative square root 5 divided by 5 to the second power, and then math, enter, enter, tells us that's 1/5. Okay, so anyway, back to this. Plus cosine squared theta equals 1. If I subtract 1/5 from each side, cosine squared theta equals 4/5. So take the square root of both sides, and we know it's going to be negative. So that's the negative square root of 4, which is 2, over the square root of 5, which we'll have to rationalize. But once again, I've applied that knowledge of quadrant 3 to get a negative value. So let's continue this on down here and say cosine theta is negative 2 over the square root of 5, but if I rationalize, I get negative 2 on the square root of 5 over 5. So there we have both the sine and the cosine from that initial information. And that's some real chapter 5 stuff right there. If you were able to follow that argument, no problem. You're where you need to be coming out of chapter 4. If I said about 10 things you don't know what the heck I was talking about, you probably slacked a little bit on chapter 4. And you might say, "Ooh, chapter 4 test not due till Friday. I won't even look at it till then." Bad choice. Because we already moved on from that. All right. So we have cosecant theta and cotangent theta. Those are the ones we want to find. And our given information is tangent theta is negative 4 over 3, and the cosine of theta is negative. So these two pieces of information, I could create a reference triangle and solve this real quick. But let's do a quadrant analysis. First of all, tangent is negative. The tangent is only negative in Q2 and Q4. That's where the sine and the cosine have different signs, SIGNs, positive or negative. So in quadrant 2, the x or the cosine is negative, the y or the sine is positive. And then in Q4, the x or the cosine is positive and the y or the sine is negative. So that's why I know it has to be one of these two. Then the cosine negative, well, that's only the case in Q2, so we can disqualify Q4. We know theta is in Q2. And we know the tangent of theta is 4/3. So that's going to tell us the cosine is negative, the sine is positive. So in relation to the cosecant, so the cosecant is 1 over the sine. So this is going to be greater than 0 in Q2. And then the cotangent is going to be negative in Q2. So we know when we find these, this will have to be positive, this will have to be negative. And that sine, S-I-G-N analysis is so important because when you take the square root of a thing, you don't know if it's positive or negative. All right. So tangent theta equals -4/3. Let's see. If we want sine squared theta plus cosine squared theta equals 1, we want to algebraically manipulate this in some way that gives us the tangent. Remember that the tangent is the sine over the cosine. So let's just do cosine squared theta, divide everything by cosine squared theta. That's going to give us some trig identity that includes the tangent. So I've got tangent squared theta plus 1 equals secant squared theta. Secant isn't one of the ones we need, but that's okay. We'll get the cosine that way, and we can use that to find the sine. And once we have the sine, we can get all of it. Okay, so plugging in the tangent that we know the tangent is -4/3. So that's 16/9 plus 1 equals secant squared theta. 16/9 plus 1 is 16 plus 9/9. And then 16 plus 9 is 25/9. And so the secant of theta is going to be the square root of 25 over the square root of 9. But let's think about where we're at. We're in Q2, and the secant is 1 over the cosine. Cosine's negative. That should be -5/3. And that tells us, because I know the secant is 1 over the cosine, -5/3. So the cosine itself is -3/5. So this tells me cosine. All that work, we finally got to where we know the cosine. So all that was about finding the cosine. Now let's use that to find our real target, which is the cosecant and the cotangent. Well, the cotangent is going to be pretty easy because the cotangent is 1 over the tangent. So let's find the cotangent real quick, since that's the easy part of this whole thing. So tangent theta is -4/3. We can use the reciprocal identity. And then we reciprocate both sides. And we get -3/4 for the cotangent. So there's part of our answer. And now we need to find the cosecant. So to find the cosecant, I need the sine. I've got the cosine. So finding the sine, I can use the Pythagorean identity again. Remember that sine squared theta plus cosine squared theta equals 1. And there's often in chapter 5 the case that there's a very efficient pathway to the solution, and I don't just happen upon it. And so sometimes I'm doing a little circuitous route. So there will be some trial and error involved in applying these identities, because there's no like sign at the top of the problem that says use this certain identity. Some are more efficient than others in solving certain problems, and you don't tend to know that till after the fact. But anyway, here we go. So let's plug this in for the sine, or for the cosine rather. So we've got the sine squared theta plus -3/5 squared equals 1. So sine squared theta plus 9/25 equals 1. If I subtract that from both sides, that tells me sine squared theta equals 1 minus 9 over 25. Actually, that should be 25 over 25. Tell Chase to have a seat and start taking notes. What are you doing with your life, son? 25 minus 9 is 16. But that's sine squared theta, so I need to take the square root. So sine theta is going to be the square root of 16 over the square root of 25. But again, think about where we're at. We're at Q2. Okay, yeah, it's positive there. So now we need the cosecant. One more trig ID in this lengthy problem. So 1 over the cosecant theta is 4/5. Applying the reciprocal ID here. Sine is 1 over the cosine. And now I take both sides to the negative 1 power, and I see the cosecant of theta is 5/4. There probably was a more efficient way to get to those, but that's what I happened upon. Yeah, you're using trigonometric expressions as algebraic entities.
I feel like it's not that hard. There's just a lot of stuff.
It brings together the first 3 chapters in chapter 4. So again, we're performing algebraic manipulations on trig expressions. So you're using the sine of x like you used x in chapter 2. I think you'll find them interesting, these problems. At least I do. Okay, so cofunction identities. You remember I told you guys that these relate to the graphical relationship between sine and cosine. You will have these on a document, so there's no need to write them down. They're also in your text in the first section of chapter 5. But it is important to understand where they come from. Notice that each of these represent a phase shift of another trig function. So this is about the similarity in shape. You probably noticed cosecant and secant had the same relationship. They were just each other shifted to the left or right. And you probably noticed that with tangent and cotangent as well. So anyway, the graphical relationships between these are what cause these to be true. Odd even identities. This is the oddness or the evenness of the trig function and how you can use that to create an identity. So remember the graph, it's either symmetric to the origin or symmetric to the y-axis. If it's symmetric to the y-axis, as in the case of sine, you get this sort of identity. If it's symmetric to the origin, cosine is symmetric to the y-axis, you get this. Sine is symmetric to the origin, you get this sort of identity. So the sine of negative theta is negative sine theta. You remember the definition for odd and even functions? So that's where this comes from. Let me just refresh your memory real quick. If a function is odd, f of negative x equals negative f of x. You see how that relates to this? How this is what makes this true? And then the definition of an even function algebraically was f of negative x equals f of x. And so you see how that's where that comes from. So oddness is what creates these, and evenness. And here you see the tangent is odd. So symmetric to the origin. Okay, so anyway, if cosine of x is negative 0.75, we need to find the sine of x minus pi over 2. So, first of all, we need to rewrite this left side of the expression in a way that relates to cosine. And if we use our identities that we were just presented with, remember that the sine of theta, so this is one we'll use. Sine of theta is the cosine of pi over 2 minus theta. So we'll use that one. And we'll also use, let's see, the cosine of negative theta is cosine theta. That'll do it for us, I think. Glad they wrote that sound into the software. Shutter sounds are so great. Really show off what it can do. I once had a real bad day as a consequence of a shutter sound. Remind me and I'll tell you later. It involved a YouTube celebrity. Okay, so first of all, we've got this, but do you see how these two values are the opposite of this? So what I need to do is say, actually, I grabbed the wrong one. I'll have to grab another one, but that's okay. The difference, if I flip a difference, it creates the additive inverse. So let's say a difference is 5. 7 minus 2. What is 2 minus 7? Good. Let's say a difference is 8. 10 minus 2. What's 2 minus 10? So you see, when I flip a difference, I create the additive inverse. So I can write it like this. If I throw this negative out here, and then we'll need this identity. I grabbed the wrong one. Say cheese. That was the shutter sound on my own phone. Feature phone back in early 2000s. You guys were still kindergartners or something. So the sine of negative theta is negative sine theta. So I can say this expression is equal to negative sine of pi over 2 minus x by applying that identity. And then if I go up here, the other identity I've saved, come on down. You guys ever watch The Price is Right? Come on down. So if this is true, then the negative, well, actually, we got the wrong one again. That's okay. We'll get where we need to be. So I need the cosine from that other list. This one. This is the one that's going to be most efficient. There we go. So that's the most efficient way to solve it. Because you see how if this is true, then negative cosine theta has to equal negative sine of pi over 2 minus theta. This leads to that. And then here, I see this is the same as this, just theta and x are interchanged, which is okay. So I know that this expression is equal to negative cosine of x. And we know that cosine of x is negative 0.75. So this is going to be positive 0.75. That's our answer. So we applied several of those identities and arrived at our solution. I could have used those other ones, but it would have been a more circuitous path. There will be a time in chapter 5 where you frustratedly apply several identities, and then you wind up with a more complicated expression than you started out with, and then you just kind of throw your pencil across the room, scream in fury, and close your book, and then start playing Call of Duty. So that's going to happen. Expect it to happen. These problems are frustrating for everybody. I once had a student teacher years ago who chose a very challenging trigonometric section to teach. And I advised against it. I said, you know, when the teacher's observing professor came in, I advised against it. I said, dude, you better pick something a little easier. He said, oh, no, I got this. So the poor fella came up, worked the problem, took about 45 minutes. And at the end, he realized he had made a mistake somewhere before because it didn't match up with the answer. So the kids had just taken notes for 45 minutes. And he's like, oops, sorry, guys, that was wrong. Let's start over. You can imagine how the students reacted. And I love the kid, and he now he didn't. It didn't compromise his ability to become a teacher because he's now a teacher at Unicoi Middle School. But a life lesson, I think, well learned in his case.
Why is he teaching pre-calculus if he's going to teach at a middle school?
Because the same license that allows you to teach in 7th grade allows you to teach pre-calculus. We do not differentiate. 7 through 12 is considered, if you're highly qualified to teach math, then you're highly qualified to teach 7 through 12. Now, the people that are strongest in content tend to teach what I teach. People that are strongest in pedagogy tend to teach 7th grade. Teaching 7th graders is a whole different challenge. It's not easy. The material's easy, but teaching them's not easy. Think about yourself in 7th grade. How eager were you to pay attention? How important was it that the teacher had good classroom management skills? So people that are very strong in pedagogy, which he was, go to the lower grades typically, and people that are very strong in the content are typically better at this kind of stuff. Because I don't even have to worry about you guys acting up, because if you don't pay attention, well, you're going to bomb the test, and that will work itself out, if you know what I mean. All right, so I don't think we need another one of those. But this would be an application of those same identities you saw me just do. So let's work this one out. Simplifying expressions. This is something we love to do in chapter 5. Simplifying these expressions. In other words, rewriting them with fewer terms, maybe, or simpler terms. My first and default strategy is always to rewrite as sine and cosine. So that's my default strategy. Occasionally, other strategies will be more advantageous for whatever reason. But this is my default strategy for simplifying a trigonometric expression, and it'll work 90% of the time. The times when it won't work is when you have multiple powers of a trig function. That's when you got to get a little fancy, use the Pythagorean IDs and so on. Even then, it sometimes works, but higher powers, or if you have some algebraic weirdness like a trig function under a root or something. So for a simple expression like this, this will generally be your best strategy, generally. So let's do that. I know that the cosecant is 1 over the sine of x, and then the cosine x is already in terms of sine or cosine. And then the cotangent is the cosine of x over the sine of x. So I've got this. Let's see here. So I've got 1 over the sine of x minus, and then if I multiply these out, I get cosine squared x over sine x. I see where I'm going with this. Sometimes in sports, a play begins to unfold, and you've got enough experience and skill to see what's going to happen in the near future. You know what I mean? Like you're breaking towards the basket in basketball. You know the defender's already a step behind you, and you're going to have a clear path for a layup. Or in baseball, the pitcher throws the 3-2 pitch, and as it leaves his hand, you realize it's a strike down the middle, and you can swing away and get a home run. So sometimes you can see the near future. And here I see the near future we've got this problem licked. Because I can factor out 1 over sine of x, and I get 1 minus cosine squared x. And you might say, well, what the heck is the use in that? Well, remember that sine squared x plus cosine squared x equals 1. That's our Pythagorean identity. If I subtract cosine squared x from each side, I get this. So you see how I can replace this with this. So I have 1 over sine x times sine squared x. And so I have sine squared x over sine x. 1 power of the sine will cancel. And there's my answer, my most simplified answer. Satisfying when it's something simple like that. When it's not, you question yourself, don't you? You ever solved a math problem at some funky decimal or fraction? You're like, ooh, this can't be right. But then sometimes it is. So I started out by rewriting it in terms of sine or cosine. It just helps me see the relationships. And then I saw that both of these terms have sine x as a denominator. So I factored out 1 over sine of x, which left me 1 minus cosine squared x. And then I applied this alteration of the Pythagorean identity to get to the next to last step. And then I canceled out 1 power of sine of x to get to the final step. So questions about any of this? How are we feeling about chapter 5 so far?
At first, I was feeling great. Now I'm feeling not too great.
It's okay. It will require, as I said, whatever time you've allocated in the past, probably a little more for chapter 5. And again, it's a short chapter.
The only thing for me is like learning all the different functions that you gotta plug it into. Once I figure all those out and like get those somewhat memorized, it'll be way easier.
Yeah.
It's just figuring out where to plug it in and what to.
Yeah, you've happened upon the key, which is knowing which trig ID to use. And I'm telling you, there will be a time where you'll use the wrong one, and the result will be a more complex expression than you started out with. And you'll sling your pencil, shut your book in frustration, and find some other activity to do for a while. That's okay. We've all been there, myself included. So here we go. Cosine squared x times sine x minus the cosine, and 90 is pi over 2 in radians. So I'm going to change that to pi over 2 just because that's the way it's written on the IDs. So 90 degrees is also pi over 2. If I go back to these cofunction IDs, notice that, no, not those. Cofunction IDs. Notice that the sine of theta is the cosine of pi over 2 minus theta. So let's just steal that one. Here's where we are. Wow. Very counterintuitive the way that way. So we see that this expression is just like this, so we can replace that with this value. So cosine squared x times sine x minus sine x using this cofunction ID. And now I can factor out the sine. So here we've got a Pythagorean application. Anytime something's squared, like I said, your default should be the Pythagorean ID. And I know that sine squared x plus cosine squared x equals 1. If I subtract sine squared x from each side, I get this. So, well, actually, I need to subtract cosine. Then. So subtract cosine from each side to get sine squared x equals 1 minus cosine squared x. And you remember my additive inverse argument when I flip a difference? 10 minus 2 is 8. 2 minus 10 is negative 8. So if I flip this difference, I just make the other side negative, and that works out. So remember, 10 minus 2 is 8. 2 minus 10 is negative 8. You see the relationship here? Okay, so that tells me, because these are the same expression, I can plug this in for it. So this is also sine of x times negative sine squared x, which is negative sine cubed x. Oh, that was a nice one. Another satisfying problem. I'm glad. I'm just kind of pulling out every trick I've taught you all at once here. Bringing it together. All the things we learned in our algebra sections and all the things we learned in chapter 4.
Is that 3x?
Negative sine cubed of x. So that's a superscript 3, meaning to the third power.
And you got that 2 more.
So you had 2 powers of sine inside the parentheses, 1 power outside. When I simplify it, it's 3 total powers. And then a positive times a negative is negative. So good questions. Example 5, we're just about done. And I know this has been a lengthy and a challenging section. But we're going to do one more. So we've got secant, don't leave that c off, of x over 1 minus secant of x minus secant of x over 1 plus secant x. So when you have this situation, we want to combine these fractions, but we've got different denominators. So in order to make those denominators match, I need to multiply each by the other. So what I'm going to do, I've got secant x times 1 plus secant x over 1 minus secant x times 1 plus secant of x. So if I multiply the left, top and bottom, by the denominator on the right, and then I multiply the right, top and bottom, by the denominator on the left, the result is going to be hopefully something I can simplify. So I've got secant x times 1 plus secant x over, this is a difference of squares. So remember that this little shortcut, a minus b times a plus b is a squared minus b squared. So that's the old difference of squares trick I'm going to use with this denominator to simplify it. So that's going to be 1 squared, which is 1, minus secant squared x. I don't have to FOIL it out or anything because I see that relationship. Minus secant x times 1 minus secant x over once again, 1 minus secant squared x. So now we have a common denominator. And there's a trick we can use, which is if I say A over C minus B over C equals A minus B over C. In other words, if I have two fractions with the same denominator, I can combine the numerators, write it as a single term. So let's do that. So I get secant x times 1 plus secant x minus, and you have to be careful here. So easy to make a sign error because we're subtracting away all this stuff. So put some sort of delineator around it to indicate that. Like so. And all that is over 1 minus secant squared x. Now we've got the fractions combined. From this point forward, it's only algebraic simplification. Well, there's one more identity we're going to apply, but not as challenging as what we've done so far. So I'm going to distribute here. Secant x times 1 is secant x. And then secant x times itself is secant squared x minus. And then secant x times 1 minus secant x times itself. And then that's 1 minus secant squared x as the denominator. So now I need to distribute that negative sign. Like so. So you may notice that something cancels in this numerator. What is it, Alden? Secant x goes away. And then I can combine these to be 2 times secant squared x. So we're really close now. I told you we'd have to apply another identity. And it's down here, 1 minus a squared term should always scream Pythagorean transformation to you. So sine squared x plus cosine squared x equals 1. How can we change that to be the secant? Well, the secant is 1 over the cosine. So if I divide everything by the cosine, I'm going to wind up with some expression that involves the secant. So sine over cosine is tangent. Don't change your argument. I'm bad to do that. Starts as x, it should be x throughout. All right, so if I subtract 1, get this, but I want 1 minus secant squared x, so that's negative tangent squared x. So I can replace that denominator with negative tangent squared x. So if you made it to this point in a problem, I would be well pleased. Man, these are hard. But what you do from here is, to get to the next step, we'll just apply the cosine and sine strategy. So I'm going to rewrite both of these as cosine and sine. And then something will cancel out of that. So that's 2 times. Remember, the secant is 1 over the cosine. So the secant squared of x is 1 over the cosine squared of x. And remember that the tangent is the sine over the cosine. So the negative tangent squared x is negative sine squared x over cosine squared x. And I already see something I can do. I can multiply top and bottom by cosine squared x, which will cancel out those cosines using the, if I divide something by itself, I'm multiplying by 1. So you see how if I do this to the top and the bottom, I have effectively multiplied it by 1 and changed to nothing. Just rewriting it in a different way. So that tells me this is -2 times 1 over sine squared x, which is -2. 1 over the sine is the cosecant. Like so, ladies and gents. And that is chapter 5, part 1. Let me give you the briefest of brief assignments. Even my brave soldier Rachel was flagging at the end there. She always tries to stay with me on these problems.
That one problem took all my shit.
Yeah, that's chapter 5, boys and girls.
This looks like fun.
It is fun. It is. You got to embrace the challenge. You know what I'm saying? Like, are you the type of person that plays Halo on Legendary? Are you the kind that just plays it on the easy mode and watches the story?
I feel like this was easier.
You're wild.
I'm glad.
Did not like most of them.
Well, you were learning a lot of new stuff.
I don't understand any of the last chapter.
Okay, so let's see if I have the assignment. I don't have it attached on here, so let me copy and paste it from another document. Gosh, we are getting down here, guys. So here will be your task. Page 317, problems 4, 8, 11, 12, 19, 20, 26, and 27. So 8 problems. Shouldn't take you too very long. Only a couple of those are the type you saw me work out. I never want to monopolize too much of your time, but it is worth your while because I want to spare you the experience I had my first year in calculus class in college where the teachers were talking about things I had never heard. At the least, you will not be able to say that because you have heard it. Let's see.